In the ring now is number 2, Jenny McBurney, ready, yet another gamble.
Yet another gamble, ridden very well, over the leisure log, through the dew pond, getting speed wet. And that's a clear round to Yet Another Gamble.
The bay mare Yet Another Gamble is well on the way to becoming a top event horse. She has the right build for cross-country, she's quick-footed for show jumping, and she has a calm temperament ideal for dressage. Yet not too long ago, Gamble's future was uncertain.
Basically, Gamble had what is called on her eye, which was here in this region. If the sarcoid hadn't been treated, you would see a great big tumour over her eye here, which ultimately would have affected her vision in that she would have lost the sight of that right eye. She was treated and is able now to have a normal life. She's basically as any normal horse is now, which is wonderful.
This is Barney, and he's suffering from the same complaint as Yet Another Gamble. The tumour's so close to the eye that surgery to remove it would be dangerous. Another course of action's being considered.
What we're going to have to try to do is to deal with these lesions, which in the top eyelid here are the nodular form of sarcoid, which you can palpate in there. Yeah. You can feel that there's a large nodule, and ultimately, if we didn't treat this, this would burst out and create a cauliflower of very red, fleshy tissue over the front of the eye, yeah, and would obviously result in sight difficulties. What we're going to do today is to use a radiation source, which is iridium-192, which is inside a platinum-sheathed wire, which we will embed into the lesion itself.
Radiation, source, iridium-192. What's all that got to do with an operation? To begin to understand this, we have to look at the atom and its structure. A typical atom, this is an atom of the element carbon, has 3 types of particles: protons, neutrons, and electrons. The protons have a positive charge, the electrons have a negative charge, and the neutrons have no charge. There are the same number of protons as electrons, so the atom overall is uncharged. Atoms of different elements have different atomic numbers. The atomic number is simply the number of protons. For carbon, it's 6. Add together the number of protons and neutrons, and you have the mass number. 6 plus 6 is 12, so this is an atom of carbon-12. What is this? 6 protons, 8 neutrons, 6 plus 8 equals 14. Atoms of the same element with different mass numbers are called isotopes. This is carbon-14. Meanwhile, Barney's being given an anaesthetic ready for the operation. What has radioactivity got to do with him? How is it going to be used to treat him? If there are more neutrons than protons, as in carbon-14, the nucleus is relatively unstable. It has surplus energy. That sort of energy will be used to treat Barney, and it's released by a process known as radioactive decay. But how do you know it's there? You can't see anything. Or can you? Watch this. This is radioactivity in action. These trails mark the emission of particles from the source in the center. It's an isotope of radium. A more usual way of detecting radiation is with instruments. This is a scintillation counter. If we place a radioactive source in front of the sensor, the reading is around 50 counts per second. If we take the source away, the counter's still recording something. Why? This is actually background radiation. There's a small amount of radioactivity around us all the time. Barney's tumour is to be exposed to radiation emitted by a radioactive source.
So what I'm going to do now is to just introduce a pair of guide wires, which are open-channeled wires which are designed to carry the radiation source. We introduce the sarcoid wire right the way down and through the tumour and out of the skin on the other side.
If this energy is powerful enough, it will kill the cells in the tumour. But it's not quite as simple as that. Watch this.
That's the end of the procedure.
Here's a radioactive source placed in front of the detector. The reading is around 43 counts per second. Place a piece of paper between the source and the detector, and the level all but disappears. The occasional click is just the background radiation. Just a thin sheet of paper has absorbed the radiation. Here's a different source. This time, inserting the paper makes no difference. It's much more penetrating radiation. It takes a piece of metal to cut the emissions. How can we explain this? In fact, there are two types of particle emission. Some elements have many more neutrons than protons. These are the elements with large atomic numbers. For example, uranium-238 has 92 protons and 146 neutrons. The imbalance makes the nucleus unstable. It emits a particle which consists of 2 protons and 2 neutrons. It is actually a nucleus of a helium atom. This type of emission is called alpha radiation. As particles are large, they collide frequently with atoms in the paper. They lose their energy and stop quite quickly. As the uranium-238 emits the particle, it becomes a new element, thorium-234, with different mass and atomic numbers. The helium atom completes the equation. Emissions from elements with much smaller atomic numbers are different. In this process, a neutron changes into a proton and an electron is emitted. This is called beta radiation. The beta particle is very small, so is much less likely to collide with other atoms and can therefore penetrate much further. In beta emission, the mass number stays the same, but the atomic number increases by 1. The carbon-14 has decayed to become nitrogen-14. Comparing the two types of emission, the alpha particle is much larger than the beta particle. Alpha is stopped easily, beta travels further. Which radiation will be used for Barney's op?
Elaine, will you please open the radiation source?
The isotope to be used is iridium-192. It is a beta emitter. Alpha radiation would be no use in this treatment because of its very low penetration power. At the point where the radioactive material is to be brought out, only the surgeon remains in the theatre. The iridium wire has been delivered to the hospital in a lead container. It has to be handled very carefully. Why is there a need for such stringent safety precautions for the people involved in the operation? Well, exposure to radiation can be dangerous. When radiation emitted from a source strikes an atom, it often knocks out an electron. Having lost a negative particle, the atom becomes a positively charged ion. The electron it's lost collides with another atom and joins onto it, making that a negatively charged ion. In living tissue, ions can cause damage. Often cells will die or grow abnormally. In the operating theatre, it's known that the beta radiation from the radioactive iridium wire will travel only about 1 centimetre through the flesh of the horse before it loses its energy. So the cells in the tumour will be killed, but the radiation won't spread any further into healthy tissue.
Thank you very much. Horse out.
Let's look at the gears first before we do anything.
Radiation is used in other ways in the veterinary hospital. This horse, Polo, has been showing signs of lameness, but an ordinary X-ray has not revealed any bone fracture. Polo is to be injected with a solution which contains a radioactive isotope called technetium-99. Once again, safety precautions are observed in the handling of the radioactive material. The syringe, packaging and gloves will be disposed of safely. When a bone in the body is broken, even if only slightly, there is increased metabolic activity at the site of the problem. It helps to repair the damage. The solution injected into Polo also contains a substance which is transported around the body in the bloodstream. It acts as a carrier for the radioactive isotope. The presence of technetium-99 inside the body can be detected outside the body. When the detector is applied to various points on Polo's flank, a concentration of radiation is found in one particular area.
4,536.
That spot can then be more accurately looked at using a special scanner camera. But if both alpha and beta emissions have limited penetration, how is it that this radiation can be monitored? How can it pass through so much tissue and to outside the body? Here's the counter again, measuring the radiation given off by another radioactive source. It's picking up a high emission rate of 225 counts per second. Aluminium doesn't reduce the emissions at all, so there's something different about this radiation. Let's try a piece of lead. Even that doesn't absorb the emissions entirely, and the meter reading is higher than background radiation. The emission from this source has much greater penetration powers than either alpha or beta. Often when an atom loses alpha or beta particles, it's still unstable. It can lose more energy in the form of electromagnetic radiation. This is gamma radiation. Because gamma radiation doesn't involve the emission of a particle, it has much greater penetrating power than either alpha or beta.
Each of these pictures is generated by a large number of gamma emissions from the horse, which are represented on the picture as a dot. And where the dots are most dense represents where there was the greatest radioactivity in the horse and hence the greatest uptake of our bone labelling substance. And you can see on the left leg, which you know is a sand leg on the horse, we can just see the outline of the skeleton showing that even normal bone takes up a small amount of the chemical. But on the right leg, where we know that this lame leg, there's a far greater number of dots representing a greater uptake of the chemical. And this place in particular, immediately below the knee, the carpus of the horse, we can see that there's an intense discharge of gamma emissions representing a high intake.
If gamma radiation is so powerful, how can the horse survive a dose of it? After all, the isotope has been injected into the bloodstream. Let's look again at a radioactive source with the help of the scintillation meter. In the test tube is a radioactive source, a compound of protoactinium in solution. A stopwatch is started and the meter reading noted, 112 counts per second, and it appears to be falling. 60 seconds later, the meter reading is down to 63 counts. Again, the general trend of readings is downwards. Another minute on, the count is 35 and still falling. The energy emitted by this radioactive source is getting weaker. The readings can be plotted on a graph like this. The activity of the source reduces by half every 72 seconds. The time taken for the activity to fall from any value to half that value is known as the half-life. So protoactinium has a half-life of 72 seconds. Notice that activity will never cease altogether. Some radioactive sources decay very quickly, with a half-life of only microseconds. Others have a very long half-life, running into millions of years. That's a very important consideration when choosing which radioactive isotopes to use in medical treatments. Technetium-99, for instance, has a half-life of 6 hours. It's losing its power as soon as it goes into the horse, and after 4 days, it will be completely safe. But what about Barney? What's going to happen to him? The iridium isotope used in the eye operation has a much longer half-life, 75 days. After the operation, Barney is taken to a special stable where he'll be kept in strict isolation for 10 days. At the end of that period, the treatment will have worked, but the wires will still be radioactive, so they'll have to be removed and disposed of safely. Soon, though, Barney will be frolicking in the fields again with a new lease of life, just like yet another gamble.